Hi everyone. Ever wondered how your GPS finds the quickest route home or how social networks suggest new friends? It all comes down to graph algorithms, tools that model connections and help us solve real-world puzzles. In this course, you'll learn the building blocks of graphs, nodes, edges, explore key algorithms like shortest path and spanning tree, and see how they power applications from road mapping to network analysis in bioinformatics. By the end, you'll know how to turn any complex system of relationships into a graph and pick the right strategy to crack it. Ready to unlock the secrets of graph problems? Let's dive in. Building on what we've discussed, here's how we prove a problem. P is nitrogen monophosphide complete. First, we select a problem Q that's already known to be nitrogen monophosphide complete. Next, we construct a concrete polynomial time reduction from Q to P. That is, a transformation that converts any instance of Q into an instance of P. We then show this transformation preserves answers. Q returns yes, if and only if P does. Finally, we verify the entire process runs in polynomial time. Completing these steps establishes that P is indeed nitrogen monophosphide complete. Now, building on that approach, this diagram traces the chain of polynomial time reductions used to establish nitrogen monophosphide completeness for a host of classic problems. At the top sits circuit SAT, which reduces to SAT, and then to 3CNF SAT. From 3CNF SAT, the proof splits into two branches. One goes to click and the other to subset sum. Following the click branch, we move next through vertex cover, then ham cycle, and finally land at the traveling salesman problem, TSP. The key takeaway? Once we prove circuit SAT is nitrogen monophosphide complete, every arrow in this diagram carries that hardness forward, showing that each problem here is nitrogen monophosphide complete as well. Now that we've traced the reductions down to 3CNFSAT, let's dive into the classic 3SAT problem. 3SAT asks whether a Boolean formula written in conjunctive normal form is satisfiable when every clause has exactly three literals. In other words, our formula is a big AND of clauses, and each clause is an OR of three variables or their negations. Deciding satisfiability in this setting is known to be nitrogen monophosphide hard. For example, take this formula. X or not X or not X, and if X or X or X, and not X or not X or not X. Each clause here has three literals. Now the question is there an assignment of true or false to X, 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 and X that makes the entire expression true? Let's explore how we tackle that. Now that we've explored the nitrogen monophosphide hardness of 3SAT, let's turn to another classic nitrogen monophosphide hard challenge, the click problem in graphs. A click is simply a subset of vertices where every pair is joined by an edge, that is, a complete subgraph. There are two standard ways to ask about clicks. 1. The decision problem. Given an integer k, does the graph contain any click of size k? 2. The optimization problem. Find the largest click in the graph. On the left, you'll see a tiny graph of three vertices all mutually connected, a click of size 3. On the right, a larger network highlights one click in orange, illustrating a potential maximum click in that graph. Now that we've defined clicks and seen the decision and optimization versions, let's prove click is nitrogen monophosphide complete. First, click is an NP. Given a set of k vertices, we can verify in ON squared time that every pair is connected, so checking a click is polynomial. To establish nitrogen monophosphide hardness, we reduce 3SAT to click. Start with a 3CNF formula having k clauses and build a graph G as follows. 1. For each clause, create three vertices, one for each literal. 2. For every pair of vertices from different clauses, add an edge unless their literals are exact negations. With this construction, any k-click must choose exactly one vertex per clause, and no two chosen literals can contradict. In other words, a k-click in G corresponds directly to a satisfying assignment of the original formula. For example, take other X or not x or not x, and x or x or x, and not x or not x or not x. We create 3 triples of vertices, then connect only non-conflicting literals across clauses. A 3-click exists precisely when the formula is satisfiable, completing the reduction. Now let's see a concrete 3 SAT to click reduction in action on a formula with 3 clauses. We turn each literal occurrence into its own vertex. C equals x, or not x becomes vertices x, not x, not x, not x. C equals not x, or x becomes vertices not x, x, x. C equals x, or x becomes vertices x, 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 2 sex, 2 sex. Next, we connect every pair of vertices from different clauses, unless their literals directly contradict. For example, the x vertex in C links to x or x in C and to x or x in C. But not x in C never connects to any x in another clause, but a clause. In this way, any 3-click must pick exactly one non-conflicting literal per clause, and that click corresponds exactly to a satisfying assignment of our original 3 SAT instance. Building on that example, let's outline the core of the 3 SAT to click reduction. We assert that a 3 CNF formula phi is satisfiable if and only if the corresponding graph G contains a click of size k, where k is exactly the number of clauses in phi. Here's why. Assume phi is satisfiable. Each clause has at least one literal set to true. We then pick exactly one true literal from each clause and map it to a vertex in G, forming a candidate set V of k vertices. Because none of these chosen literals contradict each other, and all are true, the graph construction guarantees an edge between every pair of vertices in V. In other words, V versi is indeed a click of size k. This shows that satisfiability of phi implies the existence of a k-click in G. Now, to prove the if direction, assume G contains a click Vs of size k. We assign true to each literal represented by the vertices in V, and we can set all other variables arbitrarily. Because the click picks exactly one vertex from each clause, and by construction, no 2 vertices represent complementary literals, each clause has at least one true literal. Therefore, every clause is satisfied, and the original 3 CNF formula is indeed satisfiable. Now, let's see how we build this graph from a 3 CNF formula. We transform each clause into a set of vertices, one vertex for each literal occurrence, and then connect vertices across different clauses whenever their literals are not contradictory. In our example, we have 3 clauses. For C, x or not x or not x. C, not x or x or x. C, x or x or x, uningreat. First, we create 3 vertices for C, 3 for C, and 3 for C. Next, we draw an edge between any 2 vertices from different clauses, provided one literal does not negate the other. Legathe. Now, suppose we set x equals 0 and x equals 1 under this assignment. In C, the literal not x is true. In C, the literal x is true. In C, the literal x is also true. These 3 vertices, not x from C, and x from C, are pairwise connected, forming a click of size 3. More generally, finding a k-click in this graph corresponds exactly to picking one true literal in each clause. This completes the reduction from 3 CNF SAT to click. Now that we've seen how clicks capture one way to select connected vertices in a graph, let's turn to the complementary idea, independent sets. We start with an undirected graph G equals VE and choose a subset I of its vertices. We call I an independent set when no 2 vertices in I are joined by an edge. In the example on the right, you can see a grid of nodes and edges, with the selected vertices circled in orange. Notice that none of those circled nodes share an edge, so they indeed form a valid independent set. Building on that idea, we now formalize the independent set problem. We start with an undirected graph G equals VE and select a subset I of its vertices. We call I independent if no 2 vertices in I share an edge. The key computational question is, given G and an integer k, does G contain an independent set of size at least k? For example, in a simple triangle graph, you can pick at most one vertex. Any two would be adjacent. This decision problem is nitrogen monophosphide complete. Later on, we'll show how to reduce a 3SAT instance to an independent set instance by constructing a graph whose independent sets correspond exactly to satisfying assignments. On the right, you see a grid graph illustrating the independence requirement. Any selected vertices must be non-adjacent in this concrete layout. Now that we've seen the independent set problem, let's build the reduction from 3SAT. We start with any 3SAT formula that has k clauses. For each clause, we create a triangle whose three vertices represent the clause's literals. Then, for every variable x in the formula, we add an edge between the vertex labeled x and the one labeled not x. These are the only edges that connect different triangles. At the bottom, you can see an example with three clauses: x or x or x. Ben Yofi, not x, or not x or not x, x, master not x. The Yofi Adam yelled x, not x, or x or x. In the resulting graph, picking exactly one vertex from each triangle, while ensuring no two chosen vertices share an edge, is equivalent to finding a satisfying assignment for the original 3SAT instance. Building on that construction, let's see how we turn any 3SAT formula into an independent set instance. At the top, you'll find the key statement. The original 3SAT formula is satisfiable if and only if the constructed graph has an independent set of size k. In the middle, we've drawn three clause gadgets, one for each clause in our example. Each gadget is a little triangle whose vertices stand for the three literals in that clause. So, for the formula x or x or x, and not x or not x or not x, and not x or x or x, we build three triangles and label their vertices accordingly. Next, we add edges between nodes that represent contradictory literals, for example, between x in one triangle and not x in another. Those edges force any independent set to avoid picking both a variable and its negation. In the end, selecting exactly one vertex from each triangle, without ever choosing a conflicting pair, yields an independent set of size 3, precisely when the original 3SAT formula is satisfiable. Conversely, suppose the constructed graph G has an independent set of size k. Because we represented each clause as a triangle, an independent set can pick at most one vertex from each triangle, and to reach size k, it must pick exactly one from every clause gadget. We then interpret each chosen vertex as the literal we set to true. Since every pair of complementary literals is joined by an edge, the independent set can never contain both x and not x, so our assignment remains contradiction-free. Finally, by selecting one vertex per triangle, we ensure every clause has at least one true literal, so the original 3SAT formula is satisfied. Conversely, let's assume our 3SAT formula is satisfiable. That is, in each clause there's at least one true literal. In the graph construction, we turn every clause into a triangle of three nodes labeled with its literals, and we connect opposite literals from different clauses so you can't pick both a variable and its negation. Now, using our satisfying assignment, we choose exactly one true-valued node from each triangle. None of these chosen nodes share an edge. They lie in different clause triangles, and the only cross-triangle edges join contradictory literals, which our assignment never selects. Thus, those nodes form an independent set, whose size equals the number of clauses, completing the forward direction of the reduction. Building on that graph-based reduction, we now see that finding a clique and finding an independent set are really the same task. One is just the complement of the other. On the left, we have our original graph G with a set of shaded vertices. Notice none of these shaded vertices share an edge, so they form an independent set. On the right, we've drawn the complement graph C. Every non-edge in G becomes an edge in C. Those very same shaded vertices now have every possible connection between them, turning them into a clique in C. In other words, any independent set in G becomes a clique in its complement, and vice versa. Any click in the complement maps back to an independent set in the original. Because of this simple transformation, any algorithmic result or hardness for one problem carries straight over to the other. Building on the power of problem reductions, this diagram lays out the full chain of transformations that underpin all our nitrogen monophosphide completeness proofs. We begin with circuit-SAT and reduce it to Boolean satisfiability SAT. Then shape SAT into 3CNF SAT. From 3CNF SAT, one branch veers off to subset sum, while the other marches through a sequence of classic graph problems. First click, then vertex cover, followed by Hamiltonian cycle, and finally the traveling salesman problem. The orange box here highlights the textbook reduction from click to vertex cover, showing how a solution to one directly yields a solution to the other. At each link in this chain, proving nitrogen monophosphide completeness for the next problem depends on a polynomial time transformation from its predecessor, ultimately tracing all the way back to circuit SAT. Building on our discussion of reductions from click to vertex cover, let's dive into the vertex cover problem in graph theory. A vertex cover of a graph G is a set of vertices that touches every edge in G, meaning each edge has at least one endpoint in the cover. Formally, given a graph G and a number k, the decision problem asks, does there exist a vertex cover of size k? In the illustration, the orange nodes form a valid cover, since every edge connects to at least one orange vertex. The yellow nodes lie outside the cover. This decision problem is a cornerstone of complexity theory and has practical applications in network security, resource allocation, and beyond. Next, we'll explore the Hamiltonian cycle problem and see how it builds on what we've learned here. Building on what we've just seen, let's outline the classic reduction from k-click to vertex cover. First, observe that vertex cover lies in NP. Given a candidate cover, we can check every edge in polynomial time to confirm that at least one of its endpoints is included. Next, we describe the reduction itself. Starting from a graph G, we construct its complement graph GC by replacing each non-edge in G with an edge, and removing every original edge. This transformation runs in polynomial time. The key insight is that G contains a click of size k if and only if its complement GC admits a vertex cover of size k. That one-to-one correspondence completes the reduction. Building on our earlier reduction outline, here we illustrate the classic transformation from click to vertex cover. On the left, you see our original graph G with 6 vertices. Notice the 4 magenta nodes U, V, X, and Y. They form a click of size 4, while the 2 yellow nodes, Z and W, lie outside that click. To build the complement graph G_C on the right, we replace every non-edge in G with an edge and remove every original edge. In G_C, you'll find exactly 5 edges, and each one is incident to either Z or W. Consequently, the 2 yellow vertices form a vertex cover of size 2. Observe that 2 equals n minus the click size of 4, demonstrating that G has a k-click if and only if its complement graph has a vertex cover of size nk. Building on our previous example, on the left you see a general graph G with a k-click highlighted in pink. On the right is its complement graph G_C, formed by turning every non-edge in G into an edge. We claim that if G contains a click of size k, then G_C admits a vertex cover of size k. Here's why. Let V be the k vertices in that click, and consider the remaining vertices, VV. Now pick any edge, U, V, in G_C. By definition, U and V weren't adjacent in G, so they can't both lie in V clicks. At least one endpoint must belong to VV, which means every edge in G_C is incident to some vertex outside the click. Therefore, VV covers all edges, and since V equals k, it's a valid vertex cover of the claimed size. Building on our earlier discussion, on the left you see the complement graph G, with 6 vertices labeled U, V, X, Y in magenta and Z, W in yellow, and every possible edge drawn between them. Suppose we find a vertex cover V in G of size k, That is, we've chosen 4 yellow vertices that touch every edge. The remaining K magenta vertices lie outside V. Here's the key observation. Whenever 2 vertices both lie outside the cover V, their connecting edge cannot appear in the complement G, so it must lie in the original graph G. On the right, we highlight exactly those 2 magenta vertices and their connecting edges in G, forming a complete subgraph of size K. In other words, removing the cover from the complement leaves a set of K vertices all mutually connected in G, so we've found a K-clique. Thus, a vertex cover of size K in G directly yields a clique of size K in G. Picking up on that idea, here we see the reduction from clique to vertex cover in action. On the left is our original graph G. The 4 pink nodes U, V, X, and Y form a clique of size 4, while the 2 yellow nodes Z and W lie outside that clique. On the right is the complement graph GC. In this complement, every edge that was missing among those pink nodes in G now appears, and every original edge disappears. Notice that by selecting the 2 yellow nodes, Z and W in GC, we cover every edge. No edge remains, with both endpoints in the pink set. In other words, the size 4 clique in G corresponds exactly to a size 2 vertex cover in its complement, illustrating the classic fact that finding a K clique in G is equivalent to finding an NK vertex cover in GC. Similarly, we'll prove node cover hardness by reducing from the independent set problem. Recall that in any graph G, a set I of vertices is independent. No 2 are joined by an edge, if and only if its complement, VI, touches every edge in G. In other words, VI is a node cover. In the picture on the right, I is shaded in gray. You can see that every edge has at least one endpoint outside of I, so those outside vertices indeed form a valid cover. This perfect equivalence between independent sets and node covers gives us our reduction. Let's dive into the concept of graph isomorphism. 2 graphs, G and H, are isomorphic if there's a 1-to-1 correspondence F between their vertices that exactly preserves edges. In other words, whenever U and V share an edge in G, their images FU and F of V share an edge in H, and vice versa. Take the example on the screen. The left figure is graph G with vertices labeled A through J, and the right is graph H with vertices labeled 1 through 8. Here's the mapping F, a right-pointing arrow 1, B right-pointing arrow 6, C right-pointing arrow 8, D right-pointing arrow 3, G right-pointing arrow 5, H right-pointing arrow 2, I right-pointing arrow 4, J right-pointing arrow 7. Under this correspondence, every edge in G lines up perfectly with an edge in H. Even though the 2 drawings look different at first glance, their connectivity patterns match exactly, showing that G and H are indeed isomorphic. Building on that definition, graph isomorphism asks whether 2 graphs are structurally identical under some relabeling of vertices. It's easy to check any proposed mapping in polynomial time, so the problem sits squarely in NP. But despite decades of study, no general polynomial time algorithm has been discovered, nor have we been able to prove it nitrogen monophosphide complete. To see why this is so fascinating, take a look at these 2 10-node graphs on the slide. On the left is a bipartite arrangement labeled A through J. On the right is a square framework with an inner 4-node grid labeled 1 through 8, plus the 4 corners. At first glance, their layouts and labels couldn't be more different. Yet there exists a perfect 1-to-1 correspondence that preserves every edge, showing the 2 graphs are indeed isomorphic. That unresolved gap, neither known to lie in P, nor shown nitrogen monophosphide complete, makes graph isomorphism one of the most intriguing open questions in complexity theory. Building on that, let's now explore the subgraph isomorphism problem. We're given 2 graphs, G, and we ask, can G be found up to renaming of vertices as a subgraph within G? In other words, is there a subset of vertices and edges in G whose structure matches G exactly? This is a strict generalization of graph isomorphism, because when G and G have the same number of vertices, you recover the ordinary isomorphism question. On the left, you see a simple 4 cycle, in the center a triangle, and on the right, a larger 8-vertex graph. So can you spot that triangle inside the bigger graph? Or the 4 cycle? Determining whether such a match exists is precisely the challenge of subgraph isomorphism. Building on our earlier discussion, here's a formal definition of the subgraph isomorphism problem. We start with two graphs, G, and ask, can we find an isomorphic copy of G inside G? Concretely, is there a one-to-one mapping from the vertices of G to a subset of vertices in G that preserves every edge? This problem truly generalizes plane graph isomorphism, and, as you might expect, it's computationally hard. To prove its nitrogen monophosphide hardness, we'll reduce a handful of classic nitrogen monophosphide complete problems, 3SAT, vertex cover, clique, and independent set, into subgraph isomorphism instances. In doing so, we show that an efficient solver for subgraph isomorphism would also solve these well-known challenges. Next, we'll dive into those reductions and see exactly how it all comes together. Building on our last discussion, here's a classic reduction from the clique problem that illustrates the hardness of subgraph isomorphism. Suppose you want to know whether a graph G contains a clique of size k. You simply build a complete graph C with k vertices and run the subgraph isomorphism algorithm to see if C embeds into G. If and only if C is isomorphic to a subgraph of G, then G has a k-clique. This straightforward reduction nails down subgraph isomorphism as nitrogen monophosphide hard. By contrast, the exact complexity of the general graph isomorphism problem remains unknown. So, to sum up, we've shown that the four core graph problems, finding a clique, computing an independent set, identifying a vertex cover, and solving subgraph isomorphism, are all nitrogen monophosphide hard, meaning they resist efficient, polynomial time solutions under our current complexity assumptions. By contrast, the exact complexity of the general graph isomorphism problem remains unresolved, making it a fascinating open question for future research. Next, let's dive deeper into the graph isomorphism problem and explore why it stands apart.